All right, hey guys, I'm Mike. This is Chris, and this is Mike.
I'm Chris.
Oh, you're gonna do it this time?
I'm Chris.
We got
Hey
this
man, it's
panel
4:40. I'm awake now.
is already crap. I know. We were just talking about how we're done waking up early, but yet here we are at 4 something in the morning answering physics questions just for you. We got a good one today. We got a kinematics equation today. You ready to check it out? This is your jam.
Yeah.
Okay, so let's folks, this is the question we're doing today. It's a building question. That's not the right one. What is happening right
No.
now? That's a different one. We'll do that on a different day. Oh man. People are already just not going to watch this, you know what I mean?
Just put a timestamp.
Yeah. We're answering a lot of your questions today, okay? So we're pulling these ones from Reddit. Here we go. This is what we want. You guys want a building. God, I did it again. Why is that even a thing? We cut it out, right? We can just cut that out?
No, we leave it.
God, he leaves everything in. Why does he leave everything in? Okay, thank God. Here we go. All right, you guys, this is a classic question that you're going to get in a physics class. You're at the top of a building. You're throwing a stone straight upwards. It's going to fall back down. They're going to ask you a bunch of questions about it. You got to use all those great kinematics equations. So, you ready to do this? I'll walk you through it, Chris. You ready to do this?
Yeah, I'm a little scared, but let's go.
I think you can do it, man. Okay.
I think so too.
Okay. All right. So I'll walk him through the questions here, and we'll get after it. All right. Show me your cool tablet. What do you got?
It's pretty cool. Not gonna lie.
I bet it is. Yeah. This is only the highest tech here. You know. Yes. Untitled whiteboard. That's what I was hoping for. Yeah. That's perfect. Okay. Good.
All right. So let's read this problem. What do we got?
Okay. So you're on a building. You want to do a little picture? I always like to draw a little picture. Yeah. Draw a picture. Okay. All right. So you're standing on top. Yeah. There we go. Look at that stick figure guy. He's happy. He's throwing stones off buildings, doing dangerous things. It's good. All right. So you're on top of a building and you throw a stone upward with a velocity of 20 meters per second. That seems fast. Is that fast, Chris?
Yeah. I mean, I don't know any of the conversions to miles per hour, man. Because I mean, you never have to do that.
I know, right? 20 meters.
All right.
You know what? That's what the old Google machine's for. Okay, that's
Correct.
not that fast. It's only 44 miles an hour. That's not that bad. It's actually that's kind of weak, actually. I don't know. Throwing it straight up would be kind of tough, though, wouldn't it?
I don't know. I think so. I think I can handle it.
Okay. Yeah, get
All
that
right.
mic.
So
in
20
there.
meters. So I've got a VI. So VI.
Yeah. What do
or
you mean by
V naught.
I? Initial?
Initial. Yeah. So it's my initial velocity.
Yeah.
But see,
Yeah,
the key is I want to lay out everything that I know about this problem
I like it.
before I start. All right. What
And
else?
for those students that use not V naught, the little zero, it means the same thing. Initial, not, they mean the same thing. Okay, good. And then the building is 50 meters high. So that's the
Okay.
building height.
So I have a delta Y. Of 50
Well, maybe not a
meters.
delta
So-
Y. Maybe like a
No?
Y initial. Yeah.
Oh, okay. All right.
Yeah.
We're already
We should
wrong
do a
then.
Y initial. No, you're good. You're good. Yeah. Okay, good. All right. And the first question is, how long does it take for the stone to reach its maximum height? There we go. Big question mark.
All right. So we're looking for
What are we
time.
gonna do here? Yeah. Looking for time. What are we gonna do here? Till the max height, right? Only until it reaches the top. Chris, what's
Okay, so-
interesting about the top of the trajectory?
Well, at the top, my final velocity is going to be 0, right?
Yeah, because it's not moving, right? You throw
Yeah,
something
so
like,
it's-
hey, we're Marines, right? I got like a little artillery around here. Okay, that's way cooler than a stone. Yeah. So you fire something up, and at the very top of its trajectory, before it starts to come back down, it doesn't have a velocity for just a quick second, right?
And it's interesting to note too that even if we're on an arced trajectory,
Yeah.
in the y-axis, right? Once we
Yeah.
reach that peak, right? V final is equal to 0
In the Y direction. Yeah.
in
yeah,
the
yeah.
y direction. I mean, we still have
Yeah.
velocity in the
Yeah.
x, but in the y we're at 0.
Yeah, so if you guys haven't gotten a two-dimensional kinematics, that won't make sense. But for those that have seen two dimensions, then the y and the x velocities are not connected. They're totally separate from each other, which is tough for some folks, but that's okay. All right, so what equation are we going to use to solve this, man?
So we're looking for t,
Yeah.
and I'm looking at. So I don't have an initial velocity, right? There's no initial velocity.
No, it's 20 meters a second.
Man, oh yeah. Oh man, I can't read, dude. It's early.
Okay. I know it's so early,
dude. Well, then I want to use. Let's go ahead. Well, there's another thing that we have to understand too is that we're on planet Earth, and on planet Earth, we have an acceleration due to gravity, right?
Does the direction matter on that, by the way, when we start plugging it into actual equations?
Yeah, so it's going to, right? Acceleration is a vector, meaning that it has a magnitude and a direction. And
okay, cool.
And so in this case, gravity's working against us. So it's slowing us down. So we're going to want to go ahead and we're going to want to make sure that gravity is negative, right?
Ooh, nice deep red.
So, yep. So gravity,
okay,
or A, we can also just call it G.
Yeah, G for short. It's an acceleration. All right, good. All right, we better
so
slap all this together.
Yeah, I want to use this one. This is my favorite.
Well, we want to know. We can use that one. What's the issue, though? We don't care about delta y yet, do we?
I guess not. We don't.
That's part B. Yeah. So part A only cares about how long does it take for the stone to reach its max height, right? So
hey, I was just testing you. I was just
you got me. You got me. Yeah. That's good.
Oh, I did that messed up again. Dude, 4:30 in the morning.
That's all right. It's good. It's good. People need to see, like, that's the thing about physics is the attention to detail, right? Is taking your time, double checking things, slowing down. I like to say it out loud when I do it. I look like an insane person, but when I say it out loud, it all makes sense. Okay, good. So my final velocity is my initial velocity plus acceleration times time. I always like to call out the units. The units here should make sense, right? Velocity is in meters per second. Acceleration is meters per second squared times time, which gets me meters per second. So everything there is in units of meters per second, which is nice. And I think we can just plug stuff in. Yeah, it stops at the top. Good. 20 meters per second plus a negative.
Oh, negative. Don't forget your signs, man.
That's right. You can write plus a negative, or you can just skip straight to minus, whatever you like, right? Good. And then times time. Good. And then we can just solve that guy. Yeah?
Yeah, absolutely.
I punched it out. Ahead. I already punched it out on my calculator over here. And when we do what? We end up getting 20 divided by 9.8. And so we get 2.04 seconds. That's what I got. 2.04 seconds is what we come up with.
Why did I mess this up?
No, you're good. You divided by...
Can you show me where I went wrong?
Did I mess up or did you mess up?
I messed up. I know exactly.
Oh, I wasn't watching you. I was doing math. Yeah, add the 9.
I was doing math too.
Math for Marines. You remember that? You remember that MCI?
Yeah, dude. Well, no one ever did the MCIs legit. We just cheated. At least I did.
Yeah. Well, that's why you can't do math right now. So for those that don't know, like back in the day, in the Marine Corps, you could take like these courses. They were these thick red books of like different subjects, and you get like educational credit. And literally one of them was called Math for Marines. Like it wasn't called algebra. It wasn't called, life math or useful math or business math. It's called Math for Marines. Honestly, it had some weird stuff in there. It was a strange book. So, okay, good. So we divided that out. And what do we get? We get 2.04. That's what I got. Okay, so that's how many seconds.
And so the cool thing to understand here too is that we can cancel our units, and then so seconds squared is just seconds times seconds.
Right? Yeah, 1 over seconds divided by 1 over second squared is 1 over seconds times second squared, which gives you seconds. Yeah. And so if you're bad at algebra, it's going to be rough. It's going to be a rough road. You want to get a little practice there, right?
Absolutely.
Okay, good. You ready to do part B?
Part B.
Yeah.
Yes, sir.
Let's do part B. So part B says determine the maximum height of the stone. So now we want to use the big kahuna, as I like to call it.
My favorite.
Yeah. This is the big guy. This is like, got some distance terms. Yeah. Delta Y, V initial times T plus 1/2 AT squared. Okay, good. Yeah.
So delta Y, just so you guys are tracking, this symbol right here, delta, that's just a Greek letter that means change. Think Delta Airlines, change of location. And if we wanted to break this out, right, it's gonna be my final location minus my initial location. Exactly. Is equal to my change in location. And so if you're wondering why did I put a triangle there, don't freak out. It's gonna be okay. It's all gonna buff out.
Yeah. In this case, there's like 2 ways to solve it. We could solve the delta Y and just add that to the top of the building, or we could use the longer version, right, and plug in Y final as an unknown and Y initial is 50. It's gonna work out the same way either way. So all good. All right, so you're plugging away there. What do we got? We got initial velocity, 20 meters per second. Good. Times our new time because we know how long it takes to get there. We got the minus on the gravity. There we go. Plug that big equation in and check it out. Okay, so if we crank this out, let's see. I think I got 20.4 meters is the delta Y. So we got to be careful. Some of you might be tempted to circle that answer thinking you're done, but if you do the problem this way, you're not done because it asks the height of the stone. The height of the stone is above the ground, not the building, right? I think that's what it implies. So if the building's 50 meters high and you throw it up, it's going to go 20.4 meters above the top of the building. Yeah. Look at that. Look at that beautiful drawing. It's a masterpiece. Okay, so our total height, 70.4 meters? Yeah?
Yep.
Okay, cool. All right, you ready for C?
Yeah, send it.
This is easy. We don't even need to do any math. I think we can logic our way through this one. So C says, determine the velocity of the stone when it returns to the height from which it was thrown.
Oh, dude.
Can we answer that without mathematics? Like, and I want to drive this point home that for physics, like, I think students immediately turn to equations too often, right? You just sift through and find the applicable equation without thinking through what's actually happening. Like, I always want you to try to think through what's going on.
If I'm going to try to think, I know it's kind of dangerous, but I'm going to do it. All right.
I mean, live, that's terrifying. Right?
I'm not. Hold on. Did it say when it returns to its initial location?
Do we care?
Or when it returns to the ground?
Oh, initial location. Yeah. Determine the velocity of the stone when it returns to the height from which it was thrown. Yeah.
Okay. All right. So basically what we have to understand is in that first equation, what we were doing when we had a negative 9.8, right? So we're sucking the velocity out of that rock. And we're sucking it out at a rate, seconds times second. So every second, we're going 9.8 meters per second slower. And so since the time, right, correct me if I'm wrong, it's going to take the same amount of time to return. And that's so it would just be the opposite of negative 9.8. It would be positive 9.8, and we would reach the same VI.
Yeah, it's like it's still technically negative because it's still pointing down, but because you're getting a downward velocity, it would gain in negative velocity, right? Right. So we'll call positive velocity. Down we'll call negative velocity. So you start at 20 meters per second, and that negative acceleration bleeds off all of that velocity until you get to 0 at the top, right? But then when it falls back down, it's going to go back down the same distance. It's going to take the same amount of time. And so the equation is the same. It's still the same acceleration times time equation. You're going to end up with the same magnitude velocity of negative 20 meters per second. Why the negative? Just because it's going down now. Remember, positives and negatives are always direction. That's all positives and negatives mean. Don't get tripped up about those. It just tells you direction. But It's got to be going down at the same velocity, right? Okay, cool. Yeah. Well, that one was pretty straightforward. Last one. You ready? Ready to hit the last question here?
Oh, there's more?
Yeah, there's one more. It's a tricky guy.
Dude. All right.
We didn't rehearse that part. Yeah.
Let's go.
It's good. We can do it. Find the velocity and position of the stone 5 seconds after it was thrown. So it wants to know the velocity and position of the stone 5 seconds after it was thrown.
Oh, 5 seconds after it was thrown.
Yeah. So first, like I would say, as a sanity check, 5 seconds after it's thrown, roughly where should the stone be? Like, if we draw the picture, and we know that it takes 2 seconds roughly to get to the top.
That's easy.
Yeah. Yeah, that's the big kahuna, right?
Yeah.
We can use that for the position, but I was just thinking, like, if I was trying to help a student sanity check their final answer, because, like, sometimes, like, you can plug it into equation, you can make a mistake, you can get a crazy answer. But, like, the stone, if it takes 2 seconds to get to the top, and it takes 2 seconds to get back down to the top of the building where it started, and then 1 second later, it should be, like, below 50 meters somewhere, right?
Correct.
It should be like 30, 40 meters, something like that. I don't know. Yeah? 30 meters, maybe?
But yeah, I mean, I always round. So another trick, just round your acceleration. I mean, it's gravity, dude. It's 9.8. 10, that's good enough for government work.
Yeah, yeah.
So hey, 50, like just under 50?
Hold on this one, we still need the velocity, right? Because that's still part of the trajectory. Yeah?
Well... Yeah, yeah, it is.
Yeah. So we just start from the beginning. You just start from the beginning, and we just say, in fact, yeah, there we go. Yeah, exactly. Yeah, perfect. And now we're just plugging in 5. That's it. Like, we're still using the big equation, but now we know time. Time is 5. As before, like, we were trying to find time, yeah. Awesome. Times t or times 5. Yeah. No, not squared. That one's not squared.
I know. There.
Sweet.
There we go.
Yeah, you were trying to write seconds. I get you. Okay, good. Yeah, 20 times 5. Yeah. Okay, good. Yeah. So.
Oh, hey, I know this one.
Yeah.
What's that? This equals 100.
Killing it. Yes.
Dude.
Killing it.
Dude.
Yeah. So if you crank,
I know this one too. I know that one too. That's 25.
Yeah. And you know what? Let's just call gravity 10, 5, 125. That'll be a minus 125. You get negative 25. Yeah. If you keep the 0.8, you get 20. Oh, no, that doesn't make sense. Negative 25. I don't.
Half of 9.8 is 4.4. Right?
It's below the. It's below. It's 25, roughly 25 below the building of the height of the building because you did delta y, right? Yeah. So anyway, if you crank that out, you get and you do the delta y and you break that up and you add it to the building. Then the final answer is 27.5 meters, right? 27.5 meters. Good. Okay, good. So you crank out the math. Again, the delta y is the difference. You start at the building height, so you end up getting roughly like negative 22.5. You got to add that to 50 from the building height to get to where that thing actually ends up. Yeah, and we should actually write y final maybe instead of delta y. Yeah.
Oh yeah, you're smart.
Nah, I'm not smart. Just well practiced. Okay, and then the last thing we got to figure out is the velocity.
We have more, bro.
It's a two-parter, man. It said, want another. But here's the thing. This is what's nice. Here's what I suggest for this one. This is a little bit easier. Let's start the problem where the stone is already at the top of the building, going down at 20 meters per second. You see what I'm saying?
Yeah.
Because it wants to know how fast it's going at 5 seconds. Right?
Yeah.
But like we can just start.
So 5 seconds. So it's going 50 meters per second, and you just add the initial velocity to that. So 70 meters per second. I mean, that's a good estimation.
Am
I confusing people?
No, I don't. That's way too fast, right?
No way. It's fast enough, bro.
No, because the there's 2 seconds where it goes up and 2 seconds goes down, and none of that even counts because you end up at roughly at 4 seconds, and the stone is just being thrown down at 20 meters per second, essentially. You know what I mean?
Yeah, that's true.
Yeah, because it's got that whole like first part of the trajectory. You know what I mean? So anyway, easy way to do this. We just need another kinematics equation. Yeah. Couple different ways we can do this one. What do you think?
Read that question again.
We just want to know the final velocity after 5 seconds.
The final velocity after 5 seconds?
Yeah, I think we go right back to that first equation. V final is V initial minus GT. Yeah, or plus AT. Yeah, plus AT.
Yep.
Super easy, right?
Oh, so I see what you're saying. I get what you're saying now. So it wants to know where. It wants to know how fast it's going after 5 seconds, right?
Yeah.
Yeah, so
it's already gone up.
It's gone up.
It's gone back down.
2 seconds to get up.
Yeah.
And then it takes another 2 seconds to go down.
Exactly. That's it. Yep.
Oh, so now I get that now. We have a total of 4 seconds.
Roughly. Yeah. Where
it's back down here.
It's back to 20. So it only has one more second essentially to accelerate at that point.
So if the acceleration is roughly 10,
it should be
Can I just say 20 meters per second plus 10 meters per second?
Yeah, but it wasn't exactly 4 seconds. You know, it was like 2.04, so it's not gonna be quite right, but it should be very close to that. Yeah, it should be very close. Yeah. So yeah, final velocity is negative 20, right? Because it's going down. Oh no, I'm sorry, that was initial. You're right. Don't let me confuse you, Chris. Yeah.
Well.
Yeah, exactly. Times 5. Times 5. Yeah.
5?
Yeah, because I see what you do. You did my suggestion where we start the problem. I was only suggesting that. Sorry if I confused anybody. I was only suggesting that to help me figure out roughly what the answer should be at the end. You know what I mean? Does that kind of make sense?
It does, but I kind of like it.
Okay, well then slap a negative in front of that 20, because that's essentially what you're doing, right?
Yeah.
But
the problem though is we're not going to have the 0.04.
Yeah, I would say like
in that problem.
If you're a student and you're doing this for the first time, I would just do it from the initial start. It'll be a little bit better, easier to understand. Yeah.
All right, Mike. So walk me through it. What do you want me to do?
No, do the same equation. Yeah, you're good. V final is V initial plus AT, right? Our V initial was you threw it up at 20 meters a second, right?
Yep.
And then plus a negative 9.8 meters per second squared times your 5 seconds.
There we go.
Yeah, that's it, right? So now, in some classes, they'll let you like do 10 instead of 9.8 just so that you can do the math easy. I don't know. So we'll do 9.8 times 5. We got 49. I should have known that. Times 10 divided by 2. 49. Yeah. So minus 49. So what do you get? Minus 29 meters per second? Yeah.
That's what it looks like.
There you go. Okay, cool. And that's it. That's how you work through that problem. Not too bad?
Oh, it's horrible.
Okay, wait, we're supposed to inspire confidence, Chris. All right, so hey, for the students out there that are working on these trajectory problems and working on the equations, like I'll give you 2 pieces of advice. The first is like if your initial reaction is to read a problem and just go straight to the equation sheet and try to figure out which equation applies, you're gonna struggle, right? So like when we're doing these videos, I'm always trying to get you to look at the picture and ask yourself like logically what's supposed to happen, because you've thrown balls and stones in your life and you know what trajectories look like. So start there, right? Start there and think through the problem and think, okay, I'm going to throw it up. It's going to go to the top. It won't have any velocity for a second. It'll fall back down. At some point, it's going to pass me, right? So just like think through what's actually happening and think through the terms of how does displacement and velocity and acceleration matter, like how do they apply, right, to like what's actually going on, right? And then when it's time to sit down and do some math and find some relationships, then you can look at the equation, right?
Physics is cool, man.
Yeah.
Yeah.
I know. I think so too.
Get to draw pictures. Just make sure you draw pictures of your balls and throw them really fast.
That's right. Yeah. Good picture. Good, good pictures. All right. All right. Try that one out. Oh, second piece of advice before we go. Okay. If this is a problem I always see, I'm gonna remind people in these videos a lot. Okay. If you couldn't do the problem and you watched us solve it, and when you watched us solve it, you go, "Oh yeah, that makes sense." You don't know how to do the problem. Okay. Like watching someone else solve a problem and telling yourself that makes sense what they did is not the same as you being able to sit down and do it fresh on your own. So I highly recommend go on, do something else, take a break, come back and retry this whole thing from the start yourself to convince yourself that you know how to do it now, if that makes sense. So, all right, get after it. We need a cool end line. Like how do we end it, Chris? Goodbye. See you in the next video.
Goodbye. Goodbye.
That's so dramatic. That's so dramatic. All right. Goodbye.
Goodbye.